So, hello everyone again. This is lecture 6 part 2 of semiconductor electronics, materials, devices and simple circuits. So, in this lecture we can start with the further discussions regarding the topics about Zener diodes. So, we will understand, we will complete the complete discussion about Zener diodes and then we can move on to one of the application of Zener diodes. Okay. So, I am Sameer Lavankar, let us begin our discussion. So, currently we are on the 8th topic, that is the special purpose PN junction diodes. Okay. So, introduction is being done, classification of metals, conductors and semiconductors is being done, intrinsic semiconductor is done, extrinsic semiconductor is done, PN junction is done, semiconductor diode is done, application of junction diode as a rectifier is done, and right now we are on the 8th topic, that is special purpose PN junction diodes, in which we are currently understanding Zener diodes. Okay. So, let us understand from this topic. Okay. So, finally, we understood that this is working is, please remember this thing, that it is designed to operate under reverse biasing. Okay. Fine. So, in other words, let us start with today's discussion now. So, in other words, Zener voltage remains constant, quite evident. Zener voltage remains constant. So, as you can see that there is very little change observed in the voltage from right now. Okay. So, Zener voltage remains constant even though current through the Zener diode varies over a wide range. So, as you can see there is a variation of the current in a very wide range, but the current observed is very small. Change in current observed is very small. Okay. So, in other words, Zener voltage remains constant even though current through the Zener diode varies over a wide range. This property of Zener diode is used for regulating supply voltages so that they are constant. Okay. So, that is how we use. So, this property is used for regulating supply voltages. So, that is the only thing which we will understand in the next slide, that is how a Zener diode can be used as a voltage regulator. Okay. So, this property of the Zener diode is used for regulating supply voltages so that they are constant. Let us understand how reverse current suddenly increases at the breakdown voltage. Okay. So, now let us understand the phenomena which is happening here. Let us understand this phenomena here. So, let us understand how reverse current suddenly increases at the breakdown voltage. We know that reverse current is due to the flow of electrons from P to N and holes from N to P. So, this we know that when what does the reverse current refers to? It refers to the minority charge carriers being moved upon. Okay. So, this concept is explained clearly in the concept when we were understanding semiconductor diodes about forward biasing and reverse biasing. Okay. So, basically in reverse biasing what happens is the why is the current very small? The current was very small because the minority charge carriers were being moved across the diffusion layer. Okay. So, we know that the reverse current is due to the flow of electrons, that is the minority carriers. Where will minority carriers go from? It will go from P to N. So, electrons will go from P to N correctly because P has minority charge carriers as electrons, and similarly holes will go from N to P. Why? Because holes are the minority charge carriers in N type. Fine. So, that being said, as the reverse bias voltage is increased. So, now if we try to increase the reverse bias voltage, what happens is the electric field at the junction becomes significant. Okay. So, the electric field is basically talked about here is the depletion region. Okay. So, electric field at the junction here basically refers to the electric field at the depletion region. So, electric field at the depletion region or the junction becomes significant. When the reverse bias voltage V is equal to Vz, then the electric field strength is high enough to pull the valence electrons from the host atoms on the p side, which are accelerated to the n side. So, now this is a very important concept, this is a basic principle which is happening there. So, now what is happening is when the reverse bias voltage V is equal to Vz, then the electric field strength, this electric field strength which is happening in the depletion region is high enough. So, it pulls the valence electrons, it even pulls the valence electrons from the host atoms on the p side. So, basically there are host atoms on the p side, those host atoms would be having some valence electrons, what we can say, it attracts them. Okay. So, it basically pulls these valence electrons from the host atom on the p side, which are accelerated to the n side. So, basically those which have went to the n side, it pulls them apart or pulls them back. Okay. So, these electrons account for high current observed at the breakdown. So, that is how you can observe this current being formed here. The emission of electrons from the host atoms to the high electric field is known as internal field emission or field ionization. So, that is the process name been given here. Okay. So, the emission of electrons from the host atoms, this above thing is only been explained here. So, the emission of electrons from the host atoms due to the high electric field. Why is there a high electric field? Because we are working in the reverse bias condition. So, this emission of electrons from the host atom due to the high electric field is known as internal field emission or field ionization. Okay. The electric field required for field ionization is of the order of 10 to the power 6 volts per meter. Okay. So, the electric field required for field ionization is of the order of 10 to the power 6 volt per meter. Fine. You can see here also that the electric field in the junction was extremely high, which was of the order of 5 into 10 to the power 6 volt per meter, and similar is in this given here also, that the electric field required for field ionization is of the order of 10 to the power 6 volt per meter. Okay. Let us move on. Now, so now let us understand the Zener diode as a voltage regulator. So, basically how can this Zener diode be implemented as a voltage regulator will be understood in this slide. Okay. Now, we know that when the AC input voltage of a rectifier fluctuates, its rectified output also fluctuates. Quite evident. If let us say we have some sort of this thing in the input of the rectifier, or let us say we have some sort of this as the input wave, then the output wave will also be having some fluctuations like this. So, that is only been explained here. Okay. So, we know that when the AC input voltage of a rectifier fluctuates, its rectified output also fluctuates, correct. So, to get a constant DC voltage from the DC unregulated output of a rectifier, we use a Zener diode. Okay. So, that is the main usage of using a Zener diode. What is its usage? Its usage is to get a constant DC voltage from where? From a DC unregulated output of a rectifier. Okay. So, how it is being done? So, this is the circuit being involved here. Let us try to understand this circuit first of all. So, you can see here clearly that this was your unregulated voltage VL, and finally, the output was a regulated voltage Vz. Okay. As you can see across the regulated voltage Vz, there was a load IRL being implemented here. This was the Zener diode implemented here, and RS was being kept here. Okay. So, let us understand what is this RS and what is this RL. RL you already know, let us understand this RS here. Okay. So, the unregulated DC voltage filtered output of a rectifier. Okay. So, unregulated DC voltage here basically what is the meaning of this? Let me explain. So, this is the meaning of that output voltage which we talked about here. Okay. Okay. So, the unregulated DC voltage filtered output of a rectifier is connected to the Zener diode through a series resistance Rs such that the Zener diode is reverse biased. Okay. So, what is basically being done here, that this output voltage is connected to the Zener diode. So, as you can see, it is connected to the Zener diode through a series resistance Rs. So, this is in series with this such that the Zener diode is reverse biased. So, because these is in series, this basically is being done such that the configuration of Zener diode is such that it is in reverse biased. Okay. So, this we know that what is the basic use of Zener diode? Zener diode works in reverse bias condition. Okay. So, if the input voltage increases, the current through Rs and Zener diode also increases. Quite evident, the current will increase here also. This increases the voltage drop across Rs. So, therefore, the voltage drop across Rs will also increase without any change in the voltage across Zener diode. The voltage across Zener diode will be same only, it will be constant only, the voltage across this would increase. Fine. So, that is the essence, basically behind this Zener diode, how it is being used. Okay. So, this is because in the breakdown region Zener voltage remains constant. So, we know that the Zener voltage remains constant, therefore, even with the increase in the voltage value, this the voltage across this Zener diode will always remain same. So, this is because in the breakdown region. So, why we are in the breakdown region? Because the configuration of this resistor, series resistor and Zener diode is such that the Zener diode is acting in reverse bias condition. That is why we are working in the reverse bias, and hence we are working in the breakdown region. Okay. So, this is because in the breakdown region Zener voltage remains constant even though the current to the Zener diode changes. So, even though the current changes, so as you can see that even though the current is changing, the Zener diode breakdown voltage remains same. Fine. So, similarly if the input voltage decreases, the current through RS and Zener diode also decreases. So, current here also decrease, here also decrease. The voltage drop across RS decreases without any change in the voltage across Zener diode. So, now as we keep on doing this, the voltage across this always remains same. Current will decrease sure, but the voltage across the Zener diode will not decrease. The voltage drop across RS decreases without any change in the voltage across the Zener diode. Okay, so same thing happens for increase in the voltage also, the same thing happens for the decrease in voltage also. Okay. Thus, any increase or decrease in the input voltage results in increase or decrease of the voltage drop across RS without any change in the voltage across the Zener diode. Let me read this line again. Thus, any increase or decrease in the input voltage result. So, even if you try to increase the voltage or if we try to increase the voltage, even if you try to decrease the voltage or we try to increase the voltage, it results in increase or decrease of the voltage drop across RS. So, there will be change in the V dash position of this resistor, but there will not be any difference occurring in this. Okay. So, without any change in the voltage across this Zener diode, fine. Thus, the Zener diode acts as a voltage regulator. So, that is how you can regulate the voltage. Okay. So, this much voltage only I want. So, even if I try to decrease, the majority will be used by this resistor only, and only this amount of, let us say that V amount which is equal to this Vz will be obtained by the Zener diode, and that is how we can use this Zener diode as a voltage regulator. So, now we have to select the Zener diode according to the required output voltage and accordingly the series resistance Rs. Okay. So, that is now basic engineering only. So, we need to understand that what is the output voltage required and therefore, what is the regulator voltage required, and hence we have to engineer basically which type of Zener diode to be used and which type of series resistor has to be used. Okay. So, we have to select the Zener diode according to the required output voltage and accordingly the series resistance Rs. Okay. Fine. So, that was the complete example application of the Zener diode. We understood first of all the Zener diode, we understood the VI characteristics of the Zener diode, and finally, we understood how the Zener diode can be implemented using a voltage regulator. Okay. So, that being said, let us now understand the example regarding this this Zener diodes. Okay. So, you can see here that example 14.5. So, example 14.5 says that in a Zener regulated power supply, a Zener diode with Vz is equal to 6 volts is used for regulation. Fine. The load current is given as 4 milliampere. So, basically load current would be somewhere which is happening on this load, correct. So, the load current is given to you as 4 milliamperes and the unregulated input is given as 10 volts. Unregulated input. So, this value is given to you as 10 volts. What should be the value of series resistance Rs? Fine. So, let us understand this carefully. So, what do we want here, that the final voltage for regulation should be 6 volts. If 6 volts has to be utilized for regulation and the unregulated input is 4 volt 10 volts, then what is the amount of voltage which should be taken up by the series resistor? It should be 4 volts, correct. That would be 10 minus 6, correct. So, that should be the amount of voltage which should be taken by the resistor. Now they are just asking the value of Rs, correct. So, if we know the value of Rs, we know the value of current, we can directly calculate the value of your series resistor. Okay. So, first of all let us understand, so please remember this is your load current. Okay. The current which is passing through the load current is different from the current which is passing through the series resistor and basically Zener diode. Okay. So, that is the reason I have this example has been explained here. Okay. So, let us understand this example once and then we can move forward. Okay. So, the value of the Rs should be such that the current through the Zener diode is much larger than the load current. This is done to have a good load regulation. Choose Zener current as 5 times the load current. Choose Zener current as 5 times the load current. Therefore, the current of I which would be passing from this resistor or even this Zener diode would be having a value which is 5 times the 4 milliampere. Therefore, this value will be equal to 20 milliampere. So, you can even remember this, that the Zener current is almost 5 times the load current. You cannot use this value directly, that value is basically 5 times the load current. Okay. So, that thing being said, the total current through RS is therefore, so what is the total current through RS? The total current through RS will be nothing but equal to 20 plus 24. Okay. So, 24 would be acting in this. Okay. So, let me just explain. So, as you can see that we can apply the continuity equation here, a Kirchhoff's rule here. So, what we can say that the current which is passing through this will be equal to the current which is passing through this IZ plus IL. Now, we know this value is equal to nothing but 20 milliamperes, we know this value is nothing but equal to 4 milliamperes. So, therefore, this value should be equal to 24 milliamperes. Okay. Hope I am clear. So, therefore, the total current would be equal to 24 milliamperes. Now, what would be the voltage drop? Quite evident, if we require this voltage to be equal to what is given, we know we should require this voltage to be equal to 6 volt and this voltage is given as 10 volts, then we require this to operate under 4 volts, correct, because so that this can be operated under 6 volts and this should be operated under 4 volts, so that the complete is being used up and it is equal to unregulated voltage supply which is equal to 10 volts. Okay. So, therefore, total current through RS is therefore 24 milliamperes and the voltage drop across RS is nothing but 10 minus 6 which is equal to 4 volts. This gives RS is equal to 4 volts upon 24 into 10 to the power minus 3 which is equal to 167 ohms. Okay. So, that is how you can understand this, that is RS is nothing but equal to 4 upon, so RS is just obtained directly using the relation V by I. So, what was the V? V was 4, what was the value of I which is equal to 24 milliamperes. So, it is nothing but equal to 4 divided by 24 into 10 to the power minus 3 which is equal to 167 ohms. Okay. So, that is how you got the value of RS. The nearest value of the carbon resistor is 150 ohms. So, a series resistor of 150 ohms is appropriate. Okay. So, it is generally not 167 ohms cannot be obtained directly. So, hence the resistor which you use is basically 150 ohms. Okay. Note that a slight variation in the value of the resistor does not matter. What is important that the current IZ should be sufficiently larger than IL. So, that is the thing which matters. So, the current IZ should be sufficiently larger than this value, than this load current value or the value which is being supplied there. Okay. So, the thing which is important is that the current IZ should be sufficiently larger than this IL. Fine. Now, let us move on to the second special purpose PN junction diode which is your optoelectronic junction devices. Okay. Let us first understand what is optoelectronic junction devices and then we can move forward. Okay. So, we have seen so far how a semiconductor diode behaves under applied electrical inputs. So, basically an electrical input such as voltage was being applied and then we found out what was the output being observed. Okay. So, that was based upon electrical signals being applied. Okay. In this section, we learn about semiconductor devices in which carriers are generated by photons. So, basically all the examples such as your light emitting diode etc. would be utilized in here. Okay. So, this time there is no electrical input, there is a light input being obtained here. As you can know that what is photon? Photon is basically a light only. So, basically photons are being utilized here for the propagation in your semiconductors. Okay. So, in the working of semiconductors. Okay. So, a junction diode is being used here or a junction diode is being made. So, in this section we learn about semiconductor diodes in which carriers are generated by photons or photoexcitation. All these devices are called as optoelectronic devices. So, these all devices are called as your optoelectronic devices. We shall study the functioning of the following optoelectronic devices. Okay. So, first of all we will understand photodiodes. As the name suggests, it is used for it is photodiodes. So, photo basically tells you about detecting the optical signals. Okay. So, optical signals are being obtained here, that is photodetectors are being utilized here. Okay. Similarly, next thing is your light emitting diodes, that is LEDs. Everyone knows about LEDs, even today we have LED tubes also like this, we have LED bulbs also, we have LED TVs also. So, you know what is LED. So, what it does is it does convert the electrical energy into light. Okay. So, that is the working of the LED. We will understand LED in a quite brief detailing here. Next is the photovoltaic devices. So, photovoltaic devices are basically the optical radiation is coming to electricity, and one of the typical example which is solar cell. So, we will try to understand solar cell also in the subsequent classes. Okay. So, that being said, that is the introduction of the optoelectronic junction devices. So, let me stop this lecture here only. In the next lecture, we will start with the first discussion about this optoelectronic devices, which is your photodiode. Okay. So, let me stop it here only. We will start in the next lecture. So, thank you so much.